Welcome to Geology 108, Threats from Outer Space. The collapse of the solar nebula into a star system marked the origin of the solar system 4.5 billion years ago. The single origin of the solar system is implied by the alignment of planets on a single plane, the same rotation axis, the presence of 4 terrestrial planets closest to the Sun, and 4 gas planets, the Jovian planets, farther away. If the planets were created before and then captured by the gravitational pull of the Sun, their orbits and the type of planets would have been more random. Our Sun has the perfect size for life and should last for another 5 billion years. The planets formed quickly within the first million years after the Sun by sweeping through debris surrounding their orbits. However, there remains a large number of celestial objects that have not been captured by massive planets or by the Sun. The asteroid belt is a torus-shaped region in the solar system, located roughly between the orbits of the planets Jupiter and Mars, that is occupied by many solid bodies of varied sizes and irregular shapes, all much smaller than a planet. The total mass of the asteroid belt is approximately 4% that of the Moon. Ceres is the largest object of the asteroid belt. With a diameter of 950 kilometers, it is large enough to be considered a dwarf planet. Most of the meteorites that hit Earth originate from the asteroid belt, as interactions with Jupiter can send them off their orbit around the Sun. The Jupiter Trojans, or simply Trojans, are a large group of asteroids that share Jupiter's orbit around the Sun, but at a safe distance ahead or behind the planet's path to avoid its gravitational attraction. There are other Trojan asteroids on Earth and on Neptune's orbit. All these asteroids manifest the remnants of the solar nebula, celestial bodies that have not been incorporated into planets and moons. The Kuiper belt, located outside the orbit of Neptune, far in the outer solar system, includes small ice bodies, including dwarf planets, Eris, Haumea, Makemake, Eris, and a double dwarf planet system, Pluto and Charon, with orbiting moons. The Kuiper belt is the home of short-period comets that are made of ice with dust and rock particles. Short-period comets have a return period of 200 years or less. Long-period comets, those with an orbital period about the Sun more than 200 years, originate from the Oort cloud farther away. The solar system is extremely stable, with planets and moons following stable orbits. All planets rotate about the Sun in the same orbital plane called the ecliptic. All planets also orbit in the same direction, anti-clockwise, as seen from above the North Pole. This consistency is the result of the collapse of the solar nebula, keeping its initial angular momentum. However, there are some outliers. Earth's spin occurs around an axis that is tilted 23 degrees from the ecliptic. Earth's tilt axis is what creates the succession of 4 seasons. This is because during summer or winter, one part of the planet is more directly exposed to the rays of the Sun than the other, and this exposure alternates as the Earth revolves on its orbit. Regardless of the time of year, the northern and southern hemisphere always experience opposite seasons. If the seasons were caused by great changes of distance between the Earth and the Sun around its elliptical orbit, then both hemispheres would experience the same seasons simultaneously. The Earth's orbital eccentricity, which quantifies the deviation of Earth's orbital path from the shape of a circle, is the only orbital parameter that controls the total amount of solar radiation received by Earth. The present eccentricity of Earth is under 2%, meaning that the Earth receives similar amounts of energy from the Sun throughout the year. But this number has varied in geological history. Most planets spin on an axis that is perpendicular to the plane of the ecliptic. Uranus' spin axis is almost parallel to the ecliptic. This unique tilt causes the most extreme seasons in the solar system. For nearly a quarter of each Uranian year, the sun shines directly over each pole, plunging the other half of the planet into a dark winter. As Uranus makes a complete orbit around the sun in about 84 Earth years, the winter and summer seasons last 21 Earth years. Despite the maximum insolation near the poles, the equatorial regions are warmer, something that is still an unresolved mystery. All the planets in the solar system orbit the sun in an anti-clockwise direction as viewed from above Earth's North Pole. Most planets also rotate on their axis in an anti-clockwise direction. But Venus rotates clockwise in what we call retrograde motion, once every 243 Earth days, the slowest rotation of any planet. Only Venus and Uranus have this backwards rotation. Uranus is tilted on its side about 90 degrees, so its direction of rotation is ambiguous. Its angle of inclination is usually given as 98 degrees, which would mean that its direction of rotation is not retrograde. But if we presume retrograde motion, then the angle of inclination of Uranus would be 82 degrees. Triton is a moon of Neptune, and it is one of the few moons in the solar system known to be geologically active, the others being Jupiter's Io and Europa, and Saturn's Enceladus and Titan. Triton orbits Neptune in what is known as a retrograde orbit. This means that it orbits Neptune in a direction opposite the planet's rotation. It is the only large moon in the solar system to do this, and we are not quite sure of the reason why. The origin story of Earth and the solar system seems to be neat and tidy, except for these striking anomalies: Earth's and Uranus inclinations, the retrograde spin of Venus, and the retrograde orbit of Neptune's moon Triton. But an even more difficult observation to explain is our own moon. Small moons are pretty easy to understand. For example, Mars has two small moons called Phobos and Deimos. These two irregular objects are just a few miles across, and they appear to be nothing more than captured asteroids. The largest of the moons that orbit the outer planets presumably formed from the unclaimed remnants of planet formation. just like miniature solar systems. Earth's moon, by contrast, is relatively huge compared to the planet it orbits. Our moon is more than a quarter of Earth's diameter, and it's about 1/80th of its mass. That's uniquely large for a moon in our solar system. Our moon also does not possess any atmosphere, in contrast to Earth and nearby planets. The spin of the moon is also so tightly synchronized with Earth's that there is a perpetually dark side of the moon. The first widely accepted scientific hypothesis about the origins of the moon was the fission theory, proposed in 1878 by George Darwin, son of Charles Darwin, who proposed the theory of evolution. George Darwin's scenario imagines how the primordial molten Earth must have spun on its axis so rapidly that it stretched out and became elongated. Eventually, a big glob of magma was ejected off the surface into orbit. On first hearing, this idea seems plausible enough. For example, when soft, elongated objects like pizza dough spin too fast, they split apart in two. The fission theory is then a dramatic expression of centrifuge forces. The second competing idea is called the capture theory. In this reasonable model, the moon is thought to have formed separately as one of the numerous smaller planetesimals that occupied more or less the same distance from the sun in the emerging solar system. At some point, as the story goes, the two orbiting bodies passed close enough to each other so that the Earth captured the smaller moon. This scenario is compatible with the accretion of planetesimals to form planets early on in the solar system. This mechanism is plausible for small moons that feature a similar composition as the planet they orbit. The third hypothesis, and perhaps the least dramatic one, is called the co-accretion theory, which suggests that the moon formed more or less in its present location and at about the same time as Earth. In this view, planets form around the sun from its leftovers, and then moons form around planets in exactly the same way from their leftovers. It's almost certain that the big moons of Jupiter and Saturn formed this way. It's a common theme seen over and over again in the solar system. Smaller objects accrete from clouds of dust, gas, and rocks around larger objects. For much of the past 2 centuries, the presence of the moon has proven exceedingly difficult to explain. Answers to the mystery of the moon's origin had to wait for direct sampling of moon rocks. The 6 Apollo landings between July 1969 and December 1972 featured moonwalks by 12 NASA astronauts, starting with Neil Armstrong and Buzz Aldrin. These missions resulted in the collection of more than 840 pounds of moon rocks and soil samples from 6 different sites. There were also many other key lunar measurements, such as gravity readings and seismic surveys. Research on samples from the moon has shown that the moon's mineral, while very similar in major elements to those on Earth, are rather different in detail from what we find on Earth's surface. They have a lot more titanium. The chromium is different too. And remarkably, the results of the Apollo samples cast doubt on all 3 of the competing moon-forming hypotheses: the fission theory, the capture theory, and the co-accretion theory. None of the three prevailing theories of moon formation in 1969 fit the data of the moon rocks. There must be another explanation. Three new clues from Apollo rocks place severe constraints on ideas regarding how the moon came to be. First, the moon differs dramatically from Earth in that it does not have a big, dense iron metal core. Earth's core holds about a third of its mass, but the moon's tiny core is less than 3% of its mass. This is not a trivial difference, as the moon's average density is only about 2/3 that of Earth. Second, moon rocks contain almost no traces of the most volatile elements, for example, nitrogen, carbon, sulfur, and hydrogen, which are so common on Earth's surface. Unlike Earth, which is covered in liquid water and whose soils contain abundant water-rich minerals such as clays and micas, no water-bearing minerals of any kind have been found in the Apollo moon rocks. Something must have blasted or baked the moon to remove most of those volatiles, because the moon is now an extremely dry place. The third finding of the Apollo missions is based on the element oxygen, or more specifically, the distribution of its isotopes. So, two isotopes of the same element contain equal numbers of protons, but different numbers of neutrons in their nuclei, and hence differ in relative atomic mass, but not in chemical properties. The element oxygen is found in three naturally occurring stable isotopes: oxygen 18, oxygen 17, and oxygen 16. The nucleus of each of these oxygen isotopes contains 8 protons and either 8, 9, or 10 neutrons, respectively. The key finding is that the oxygen isotope composition of the moon is indistinguishable from that of Earth. So the two bodies appear to have formed from the same stuff. This evidence proved that the fission theory, the capture theory, and the co-accretion theory were all wrong, and it didn't take very long for a new idea to emerge. The moon is now thought to have formed as the result of an epic impact with a Mars-sized planet called Theia that was competing for the same solar system real estate as Earth. The rule of astrophysics is that no two planets can share the same orbit. Eventually, they had to collide. And the larger planet always wins. Earth was bigger and won, but the moon was formed from the debris of the impact. Just after its formation, the moon was much closer and exerted much greater forces on Earth. Most models of the giant impact assume an off-center impact, in which Theia is completely obliterated and absorbed by proto-Earth, which emerge as a more massive planet. The tremendous force of the impact tilts the Earth about 23 degrees, explaining its current inclination. The impact projected an immense cloud of incandescent debris, representing an intimate mixture of the two planetary mantles. The moon coalesced rapidly, reaching more or less its present size. The physics of planet formation dictate where the moon could have formed. Every massive object has an invisible surrounding sphere called the Roche limit, inside of which gravitational forces are too great for a satellite to form. Earth's Roche limit is about 18,000 kilometers from Earth's surface. So models of moon formation place it originally at 24,000 kilometers from the Earth's surface, where it could grow in an orderly fashion by sweeping up most of the scattered bits and pieces from the giant impact. The giant impact theory is appealing because it explains all of the major clues better than any other model. The moon lacks an iron core because most of Thea's iron wound up inside of Earth. The moon lacks volatiles because Thea's volatiles were blasted away during the impact. One side of the moon always faces Earth because the angular momentum of Earth and Thea were coupled into one spinning system during collision. Along the way, our understanding of the formation of the moon gives us new insights about our anomalies in the solar system. Today, the retrograde spin of Venus, the inclination of Uranus, and the retrograde orbit of Neptune are all thought to be the result of other giant impacts with these planets during the early stage of the solar system, when the sky was crowded by many more celestial objects. The moon formation was a pivotal event in Earth's history with far-reaching consequences that are utterly amazing. The moon of 4.5 billion years ago was not the romantic silvery disk that we see today. Long ago, it was a far more looming, dominant, and unimaginably destructive influence on Earth's near-surface environment. The moon formed only 24,000 kilometers from the Earth's surface. Today, by contrast, the moon is 385,000 kilometers away, about 16 times more. It seems at first blush utterly impossible that a giant moon could just drift away from Earth like that, but measurements don't lie. About 4.5 billion years ago, the moon filled the sky, dominating the view of the cosmos, and it orbited Earth every few days. In addition, Earth rotated on its axis much faster than today. A day lasted about 5 hours. About 4.5 billion years ago, the moon orbited Earth every few days. In addition, Earth rotated on its axis much faster than today. A day lasted only 5 hours, and there were more than 1,750 days per year. Yes, you heard right. The sun rose every 5 hours, 4.5 billion years ago. Such an estimate seems bizarre and untestable, but at least a couple of direct measurements confirm this idea of shorter ancient days. Finely layered sediments called tidal rhytmites reveal the daily, lunar, and yearly cycles of the tides. Microscopic studies of tidal rhytmites from 900 million years old rocks in Utah point to a world where Earth days were only 19 hours long, when there was 464 days every year. The calculated Earth-Moon distance of 350,000 kilometers at that time implies a recession rate very similar to that of modern times, about 4 centimeters per year. Indeed, pointing lasers to the moon has allowed us to measure how fast it moves away from Earth every year. Complex gravitational interactions have caused the Earth-Moon distance to increase, and it is still increasing today. The moon is thus an integral part of Earth's evolution, and it carries a unique record of that evolution. Collisions between Earth and astronomical objects has been occurring since the formation of the planet. The collision with Theia, followed by moon formation, is the most dramatic, life-altering event of Earth. This has been followed by a late heavy bombardment 400 to 700 million years after the planet formation, a time during which a disproportionately large number of asteroids may have collided with the early terrestrial planets in the inner solar system, including Mercury, Venus, Earth, and Mars. Evidence for the late heavy bombardment derives from lunar samples brought back from the Apollo mission that show that most impact occurred in a rather narrow interval of time. However, the samples were from a single impact crater and may be biased. A great many impacts from astronomical objects, large and small, have occurred throughout Earth's 4.5 billion years history. In fact, every year, the Earth is hit by about 6,000 meteors large enough to reach the ground, or about 17 per day, most of them coming from the asteroid belt. These objects reveal the composition of the solar system and have great scientific value. They are commonly found in large desertic areas like Antarctica, the Sahara Desert, or the Arabic Peninsula. While asteroids' impact is commonplace, some have strong repercussions. After the collision with Theia, the most impactful one is the asteroid impact that occurred 65 million years ago, leaving a giant impact crater at Chicxulub, Mexico. The debris from the collision spread throughout the globe in the upper layers of the atmosphere, obscuring the Earth's surface. The dust from this giant cloud can be found in the sediment record throughout the planet, marked by a high concentration of iridium. The reduced insolation stressed the food chain, leading to a mass extinction event, and notably the extinction of all non-avian dinosaurs. This cataclysmic event marked the end of the reign of the dinosaurs, allowing the primates to take dominance, the culmination of which is the rise of humans some 60 million years later. The Younger Dryas impact hypothesis proposes that the impact of one or more large comets initiated the Younger Dryas cold period about 12,900 years before present. The Younger Dryas ice age lasted for about 1,200 years, causing megafauna extinctions before the climate warmed again. The Hiawatha Glacier's impact crater in Greenland is offered as evidence for the Younger Dryas impact hypothesis. Giant craters can be found closer to home. The Meteor Crater, a colossal hole in the Arizona desert, formed 50,000 years ago by impact with an iron meteorite about 50 meters in diameter. It left a scar on the Earth's surface with a diameter of about 1 kilometer, a depth of 170 meters, and a rise along the rim of 50 meters, revealing the destructive potential of asteroids. Threats from outer space are very real. Planetary defense encompasses all the capabilities needed to detect the possibility and warn of potential asteroids or comets impacts of Earth. However, further impacts with major meteors is ineluctable, and it's just a matter of time. Chances are excellent that you don't have to worry, nor most likely will any of the next 100 generations. But we can be absolutely sure that another big impact of the dinosaur-killing variety is coming someday, somewhere. In the next 50 million years, Earth will suffer at least one big hit, maybe more. The most likely culprit are also Earth-crossing asteroids, objects with highly elliptical orbits that cross the plane of Earth's more circular path around the sun. At least 300 of these potential killers are known, and in the next few decades, some of them will pass uncomfortably close. In 1995, an asteroid whizzed by within a few Earth-Moon distances. In 2004, asteroid Toutatis, an elongated 1.5 by 3 mile object, passed even closer. And in 2029, asteroid Apophis, a 900-foot diameter rock, is predicted to cross much closer still, well inside the moon's orbit. For every known Earth-crossing asteroid, there are probably a dozen or more yet to be spotted. And when one of these projectiles is finally observed, it will likely be much too close for us to do anything about it. To survive in the long run, we must journey outward to colonize neighboring worlds, first the moon and then Mars.